The topic for today's video. We're going to do solving other types of equations. And a lot of this is going to be review. Some of you guys have been asking for more review on some of the stuff we've already covered. So I'm going to use this as an opportunity to review stuff, but then there's also going to be new things. So there's four main topics here. The first one has a bunch of different subtopics. So the first one we're going to do is solving equations by factoring, and we've already done a lot of that. So there's factoring out the greatest common factor. There's quadratic equations when a equals 1 and a doesn't equal 1. Difference of squares, sum and difference of cubes, factoring by grouping. So that's all stuff from previous. But then we have a new topic right here, which is factoring in quadratic form. And like the name implies, it's going to take quadratics and just add a little something extra to it. But it's not too bad. It really isn't. Then we're going to do solving radical equations, which I believe is review. We're going to take it a little step further, but it's still not that hard. Solving rational equations will probably be a new topic. And then solving absolute value equations is also review from integrated 1. So although this looks like a lot of stuff in here, there's really only two new things. And what I'm going to do is, that's a little different than what I've done before. I'm going to go ahead and give, once I finish recording, I'll figure out the timestamps for when I get to these different topics. So if there's something that you already feel really comfortable with, you don't want to review, you can skip that and go right to the topic that you want to see. Okay, so with that said, really what today's video is going to be is a ton of examples. And there's going to be a lot where I'm just going to say, try these on your own, pause the video, and then we'll look at them together. So it will give you a lot of practice, because again, that's something else that you guys have been asking for. Okay, so let's take a look at the first thing. Oh, by the way, one thing I am going to do though, this factoring out the greatest common factor, I'm just going to kind of weave that into these different topics. So I'm not going to separate that one out. Okay, so let's look at our first example. All right, so here's the first example. It's pretty much review, so I'm not going to say anything else about this. I would encourage you guys to pause the video and just make sure you can do this one on your own. And in a moment, I'll reveal the actual solution. So pause the video right now. All right, so this is what you should have gotten. And again, just real quick to go through it, there is a common factor of 2x and everything, so I factored that out. Don't just divide it out and forget it though. This is important. You can't just get rid of it. So some people forget to write that. But then you factor what's left, and I just did the x thing right here, the Australian method. A times c in the top, b in the bottom. What multiplies, whoops, I should have a negative on that, 8. What multiplies to positive 8 but adds up to negative 9 is negative 8 and negative 1. But then divide them by a, so that's why I divided everything by a. This fraction reduces, and then I have my answers. Remember, read them from the bottom up. 2x minus 1, x minus 4, and that's where those came from. Then you just set each factor equal to 0 and solve. So there's our first example. Okay, let's go to our next one. All right, so here's the next one. Again, you should be able to do this one on your own, so if you want to go ahead and pause the video, think about solving this by factoring, and in a moment, I'll reveal the solution. So you can pause it right now. All right, so here's the solution. Oops, and I just realized I forgot one little thing. The one thing you're going to want to do is make it equal 0 first. So we're going to have to move this 75x cubed by subtracting it. And so that makes this side equal 0. But then once you do that, we can start factoring. And there is also a greatest common factor of 5x cubed. You're left with a nice simple quadratic where a equals 1. So what adds up to negative 2 but multiplies to negative 15? Negative 5 and positive 3. Set each factor equal to 0. Solve, and you get those three answers. All right, second example down. All right, let's look at the next one. All right, so here's the next one. So there's different ways you could factor this, but what I want you to focus on is let me back up. There's different ways to solve this equation, but I want you to focus on solving by factoring. So get that factoring practice in. So factor that, see what you get, pause the video, try it on your own. All right, so here we go. Now this one ended up being difference of squares, and it ended up being difference of squares twice. So we were able to factor it first using difference of squares, but then this one was difference of squares again. So we could factor it again. This one doesn't factor though, so we leave it alone. So now we've fully factored it, set each factor equal to 0, and then solve. Now this one was kind of special. We wound up with some imaginary answers. So we had 2 real answers and 2 imaginary answers. So pay attention to directions. When I give a test, I'm going to make it very clear if I want real solutions or all solutions, and all solutions would imply to include the imaginary solutions. If I ask for just real solutions, then obviously don't include the I. But if I ask for all solutions, include the imaginary ones or complex answers in there as well. Now, I say that I think, if I remember right, that your textbook is going to say find all solutions, but I don't think they want the I. So anyway, just kind of keep that in mind. It's just, there's no, technically if they say all solutions, they really should be including the imaginary and complex solutions in there as well. But I believe they're a little inconsistent on this one. I could be wrong though, I might be remembering that wrong. Anyway, there's this problem. Okay, let's try another one. All right. So here's this one. I want you to find all solutions. This is going to include any imaginary or complex solutions. So again, solve it by factoring. This should be review, so you can go ahead and pause the video right now, give it a shot, and I'll reveal the answer. All right, so I have in the green cloud the formula in case you forgot it. But then it should have factored into this. Now, I will tell you this, for whenever you're doing sum or difference of cubes, this quadratic that you get can never be factored. In fact, I can tell you a little bit more, the solutions to this quadratic, they're always going to be a complex. So you're never going to get a real solution out of this. So this quadratic factor from the sum and difference of cubes is never going to have real solutions to it. But anyway, set each factor equal to 0, and we can still use the quadratic formula though, and you get these 2 solutions, or 3 solutions actually. 1, and then we have the plus or minus in there. By the way, if you're solving a problem like this, please do what I did. I did have, let me get my pen back here. I did have one answer here, and then I had 2 other answers here. Please don't box them separately like that and say that's your answer. It gets very confusing actually when I'm grading papers. So, and besides, it's kind of bad form. You should put your final answers together all in one spot. So please do that when you're solving. All right, let's try another one. All right, so again, I want you to solve this one by factoring, and let's say find all solutions again. So fairly similar to the previous one. So if you have trouble with the previous one, this will be another good one to practice. Okay, give it a shot. Okay, some of you might have been thinking, wait a minute, and I just noticed that too. Let's change that to a cubed. So it's 125y cubed plus 64. So give that one a shot, and we'll take a look. Okay, so here's this problem. Like I said, it was very similar to the previous one. It's just sum of cubes instead of difference of cubes. So here's the formula for that. But after that, it's pretty straightforward. You factor it, set each factor equal to 0. First one's easy. Second one, you got to use the quadratic formula, and there's your answers. All right, let's keep going. All right, so this is another solve by factoring. And again, this should be review, so if you want to pause the video, give it a shot, and we'll take a look in a second. All right, so this one ended up being a solve by factoring by grouping. And so remember, for any time you're going to solve by factoring, always got to make it equal 0 first. And then for grouping, take in this case, we're going to take 2 terms at a time. There's actually no rule that says you always have to take 2 terms at a time. But when you're factoring by grouping with only 4 terms, that makes sense. Anyway, look at the first 2 terms, greatest common factor, take that out. What are you left with? Then in the next 2 terms, take out the greatest common factor. If the first term, it's all about the first term. If the first term has a minus sign, has a negative, always factor out the negative as well. When we factor out the negative, we're also left with x plus 1, and so that's good. Remember, these have to match because then these are common factors, which factor out, and you're left with x squared minus 4, which is difference of squares, so it factors again. So here's the answer fully factored. After that, you can set each factor equal to 0 and solve. And there's that. All right, let's take a look at a few more. Now we're going to get to the new thing. So this was all review stuff, but now let's get to this quadratic form. So before we get to some more examples, let me give you some notes. Okay, so this is quadratic form. And so the deal with this is it looks very similar to what we've done before. It looks very similar to a quadratic, except this exponent's not always squared, and this exponent won't be to the first power. But this exponent is always going to be twice as big as this exponent, and that's the key. It's got to be twice as big as this one. So for instance, if I just, and I'm going to do a couple just really quick examples with you. But if I had, let's say we had x to the 6th plus 5x cubed plus 6, and I wanted to factor that. So the key to notice, well, we don't always look for greatest common factor first, but we don't have one. But then I look and I notice this exponent is twice as big as this one. So that means it's quadratic form. Now when you get the hang of it, you probably don't have to do this step in the middle that I'm going to do. But what you can do is you can actually do a little, we call it u substitution, because a lot of times we use the variable u. You can use any variable you want that's not already in the problem. But let's just say if I let u equal x cubed, and I'm picking u cubed or x cubed because that's the middle exponent, that's x to the power of n. If that's true, then I know that u squared is x cubed squared, which is x to the 6th. And now I have this part here. So now if I substitute it back in, x to the 6th I'm going to replace with u squared. X cubed I replace with u. And now it's a straightforward quadratic. We know that's going to factor into u plus 2, u plus 3. And then we can back substitute, meaning replace the u with what it equaled, and u, remember I defined that as x cubed, so it's x cubed plus 2, x cubed plus 3. And there it is factored. Now a lot of people, like I said, when you get the hang of this, you're going to be able to jump right from here down to here, but there's nothing wrong if you have to show this work to see it. That's totally fine. But again, it's totally fine also if you just go from this first step to this last step in the factoring. So the key again, this exponent is twice as big as this one. If you want to show the u substitution, if you're going to do that though, you do have to say what you're defining u to equal. You can't just jump to this step. You have to tell me what u equals. You have to at least say this. So u is x cubed, then we know that x to the 6th is going to be u squared. And then you can factor. Just don't forget to put your final answer in the same variable the original answer or the original problem was in. So that's the idea of quadratic form. So now we're going to do a few examples with factoring with quadratic form. All right, so let's try this one. So solve it by factoring. Think about what we did up above and see if you can try this one on your own. But we'll take a look at it together in just a moment. Pause the video, try it on your own. All right, so here we go. Here it is, all solved out. So again, excuse me, make it equal 0 first, but then it is quadratic form. This exponent is twice as big as this exponent. So I went ahead and did the u substitution. And again, like I said, if you're going to do that, though, define what you're going to let u equal. Don't just magically put it in there. So u is x squared. That means x to the fourth will be u squared. X squared is u. We defined that. Then I factored this. I used the Australian method. Set each factor equal to 0. And at this point, you could either solve these first and then substitute the x squared in. I went ahead and put the x squared in right now. And so this one I know is going to be plus or minus 1. This one I did a little bit of work. I had to rationalize the denominator, and I did get a negative under a radical, so I had I. And so I had these two answers there. So I put everything together, so I had these 4 answers, and there we go. So take some time and look at that if you need to, but we'll take a look at another example. All right, so go ahead, give this problem a try, and we will take a look at it together in just a moment. Okay, so here's this one. Again, make sure it equals 0 first, but then this exponent is twice as big as this one. Even though these are negative exponents, it's still the same rule. This exponent is twice as big as this one. It's still quadratic form. But notice I never actually was dealing with the quadratic equation once I got past that initial thing there. But anyway, I let u equal x to the negative 1. So x to the negative 2 is u squared. Here's my quadratic right there. But then I solve it. And when I substitute the x back in, now I actually technically have something called rational equations. We're going to look at those a little bit more later on in this video. But these are very simple ones. I'm going to isolate the x. So I get here. Remember, x to the negative 1 is the same thing as 1 over x. And there is a property that says when you have something like this, you can, if a fraction equals a fraction, you can take the reciprocal of both sides and they're still equal. Taking the reciprocal of this side, you get x. Take the reciprocal of this side, you get negative 1/2. And then I did the same thing over here. When I let u equal x to the negative 1, then solve for x to the negative 1, which is really 1 over x, and then just flip both sides and you get your answer. So there's my 2 answers right there. Okay, let's try one more quadratic form.
Okay, are you done?
Okay, so let's try this example now. Again, go ahead and pause the video, try it on your own, and then we'll take a look together. Okay, so if we take a look, then here it is. Okay, so there's a lot going on in this one. It's really the same thing. One thing is there is a common factor of x that you can factor out, and then we do have quadratic form. This exponent is twice as big as this one. So we'll do that u substitution thing again. We have something that we can solve using the Australian method, and so we factor that and substitute the u back in. And now we have these things. Now I'm going to tell you that there's a couple of things here that I won't actually test on. First of all, this is cubes, but these are not perfect cubes, the 2 and the 3. And then the same thing here, this 3 is also not a perfect cube. So these are not the sum and difference of cubes. So we can't factor that way. So when I had these, I just went ahead and isolated the x cubed, and then take the cube root to isolate it. Now I know some of you guys might be thinking, hey, wait a minute, the denominator now has a cube root in it, so shouldn't we rationalize? And technically, yes, we should. I'm not going to get into how you rationalize with anything other than square roots, though. If anybody's curious, I can show you later. I'm not going to test on that, though. So for these, they're cube roots. It's okay if we leave the denominator with a radical. One thing I do want to point out, though, is over on this one, we had a negative under the root. But this is not an even root. It's an odd root. Odd roots are okay. You pull out the negative on the outside. It's like the cube root of negative 1, and that's negative. So I do want you to pull out that negative, but it's okay if you leave your answer like that. So here's our answers for this one. Okay, so that's it for solving by factoring. So now let's move on to, let's see here, what's next? Radical equations. Okay, so let's do this first one together. In general, when you're doing radical equations, what you want to do is isolate the radical. And so that's the first thing we have to do. Whoops. We are going to do this. We're going to add 3 onto both sides. That gets the radical by itself. I don't know why I put a 3 right there. Let's change that back to an x. So we have this. And once the radical is by itself, how do you undo a radical? Well, you square both sides. And so that's what we do. The square and the square root cancel on the left, and on the right 3 squared is 9, and now you have a really easy equation to solve, and you get x is -4. Now the only thing is you have to check your answers. Whenever you raise both sides to an even power, you can introduce what's called extraneous solutions. And they're kind of a weird name because they have the word solution in them, but extraneous means they're not really solutions. So I'll write that down, but let's just check it first. Let's check x equals -4. So we have our original equation, and always go back to the original. And then I'm going to substitute the x with a -4. And whenever you show a check, even at this point, you probably see that it's going to be true, but you should, I'll do it correctly for one thing, but work it until both sides are the same, and then you know you've checked it. The other thing too that you never want to do when you're checking a solution, don't do something like, I could have added 3 onto both sides and then got 3 equals 3 at the end. You shouldn't do that. You work both sides, you simplify both sides independently. So never do something to both sides of the equation. Just simplify one side, simplify the other side, and you should get the same thing on both sides, which we do, so we're good. So this is our answer right here. So again, anytime you raise both sides of an equation to an even power, you must check for extraneous solutions. If you get an extraneous solution, don't box it. It's not really part of your final answer. So this is important. I'll highlight it a few times. Okay, so that's a general idea. We got a few examples of these we're going to go through, and yeah, then we'll go on to the next thing. Okay, so let's try this one. Same idea as what we did above. Isolate the radical first, then square both sides and see what you get. So go ahead and try this on your own, and we'll take a look together in a moment. All right, so again, you got to make it equal 0 first, so I had to move that 4 over to the other side. When you square both sides, don't forget you have to fully FOIL this thing. A lot of people forget that. So you're going to get x squared minus 8x plus 16. Don't forget that minus 8x. And then, so it is quadratic, so I'm going to make it equal 0 so we can factor. And I get 2 possibilities, but remember you've got to check them. And notice too, I'm saying check, and then I'm saying what I'm going to check. Please do that. It will tell me what you're actually plugging in there. I know it may sound obvious, like, you can see that we plugged in a -5. But it's not always obvious when people are showing their work, trust me. So if you would please tell me what you're going to check and then plug it in. And darn it, -5 didn't work. Whoops, but you know what? It's supposed to be a negative on this side. Still won't work though, so rats. 13 doesn't equal -5 either. But so I tried x equals 2, and I plugged that in, and well, gosh darn it, that didn't work either. 4 doesn't equal 2. So should go all the way down here. So it doesn't, neither one of them worked. It just meant that I had no solution. That's all. All right, let's try some more. Okay, let's look at this one together. So what do you do when you've got two radicals? Well, when you've got two radicals, you could go ahead and square both sides right now, but trust me, it's actually going to be easier if you separate the radicals. And so that's what I'm going to do. In fact, I am going to, if I can erase this. I'm going to go ahead and do it like this. Let me write it down. I'll tell you what my thought process was. So remember, my next step is I'm going to have to square both sides. Visually, this is a lot easier. If I moved this square root over to the other side, this is a lot easier to work with. It gets a little more complicated if this radical here was more complicated. It can still be done. It's not that bad. It's just easier. This is already going to be two terms. If I can not put multiple terms inside multiple terms, it just makes it easier to manipulate. But now we are going to square both sides. On the left hand, that's easy. The radical just goes away. On the right hand side, you'd have to FOIL. And I will say, if you can get the hang of, whoops, not that. If you can get the hang of squaring a binomial, some of you probably already know this pattern. This comes up often enough. It's a very handy pattern to be able to do. So whenever you want to square a binomial, just follow this. Oh my goodness. Just follow this formula here. So the 10 is my a, or 10 squared is going to be my a squared. And then I have 2ab in the middle, so it's going to be negative 20 root x. And then I should have a b squared at the end. And so it's going to be root x squared, which is just going to be root x. Now, this is always going to happen. I have a radical still left. And yeah, I do. I got to deal with that. So I'm going to have to isolate this term and then square both sides again. I had two radicals. I'm going to end up having to square both sides twice. So thankfully, it looks like the x's are just going to cancel out. So I can just cross those out. And then if I go ahead and subtract 100, I get negative 120 equals negative 20 root x. I could square both sides right now, but I notice both sides divide by a negative 20. So I'm going to have 6 equals root x. Just makes it a little easier. And I get 36 equals x. Let me go back to pink. So that's what I think my answer is. And now I should double check it. So if I check x equals 6, 36, whoops, I'm going to have the square root of 36 plus the square root of 36 minus 20. Does that equal 10? Well, I have 6 plus the square root of 16. Does that equal 10? 6 plus 4. Hey, look at that. It worked. And so that's my answer. So the idea when you got multiple radicals, separate the radicals, square both sides, isolate the term with a radical again, square both sides. But always check. All right, we're going to look at just a couple more examples and we'll be done with this. Okay, so here's one for you to try on your own. Give it a shot. We'll take a look at it together. All right, this is all there was to this one. Follow the same rules. Isolate the radical, so you have to add 5 onto both sides. This time, since it's a cube root, you're going to cube both sides to cancel it out. So here you're just left with the radicand, and 5 cubed is 125, and then subtract 1, divide by 3, and there's your answer. And that's it. You don't have to check this one because you didn't raise both sides to an even power. If you raise both sides to an odd power, all is okay. No need to check it. You could, and you're going to get the right answer. But because we raise both sides to an odd power, no need to check our answer. All right, let's try another one. Okay, so here's our last two. I'm going to look at these together because they're similar, but yet there's a little difference between them. So these are still considered radical equations because, remember, a rational exponent, the denominator means you have a root. So this means we have a cube root. This means we have a square root. Now you can go ahead and take care of all of this in once. So like over here, I'm just going to rewrite the original problem. When you have a rational exponent, you can solve it by raising both sides to the reciprocal power. And we'll raise this to the 3/2. And the reason this works, remember when you're dealing with a power to a power, you just multiply the exponents. If you multiply reciprocals, you're always going to get 1. We get 6 over 6, which is 1. So they cancel each other out, and we're just left with x plus 2. And then over here, remember the denominator is your root and the numerator is your power. So this is like the square root of 9 cubed. So the square root of 9 is 3. 3 cubed is 27. And so then we get 27. So x is 25. And there's your answer. And then over here we do the same kind of thing. Again, I'm just going to rewrite the original problem. And then we're going to raise both sides to the reciprocal power. So this is going to be to the 2/3, and this is going to be to the 2/3. And again, when you multiply reciprocals, they're going to equal 1. So a power to a power, multiply the exponents, you get x plus 3 to the first power. So you don't really have an exponent anymore that you have to write. And then the root means, or the denominator means the root. Numerator is the power, so it's the cube root of 8 squared. The cube root of 8 is 2. 2 squared is 4. And subtract 3, you get 1. Now, be careful, because there actually is something here that we need to watch out for. Can you spot it? Turns out that these are okay, but we may not have been so lucky. So what we have to be careful of is right here. We raised both sides to an even power. Remember, the numerator is like the power. We took the cube root, but then we raised it to the power of 2. So because of that, we have to check. We really should have checked this one before we boxed it. Let's check x equals 1. So 1 plus 3 to the 3/2, does that really equal 8? Well, let's see, we get 4 to the 3/2. And the denominator is the root. The numerator is the power. So the square root of 4 is 2. And 2 cubed is 8. So it does work. 8 equals 8. We were in luck. So just watch out for that. When you're using reciprocal powers, make sure to check the numerator of what you're raising each side to. If the numerator is even, you're raising each side to an even power, you do have to check your answers for extraneous solutions. All right, so that's it for the radical equations. Let's move on to our another big topic, which is rational equations. Okay, so rational equations. Rational, remember, means fractions. So these are equations with fractions. And so if we take a look, what we've got here is we have these denominators here. And this is in general what you want to do. Now, something like this, what some people do is they just change everything to a common denominator and deal with that, which this one wouldn't be so horrible. But in general, this is what you want to do. You want to find the LCD and then multiply both sides of the equation by the LCD, and that you're going to see that cancels the denominators. So let's see how this works. We'll do this one together. So always factor your denominators first. In this case, they don't factor. And because my denominators are x, 3, and 6, the LCD is just simply 6x. So that's what I'm going to multiply both sides of the equation by. Now I'm going to show some extra steps here that we normally wouldn't show, just because it becomes so cumbersome to do when the problems get more complicated. But this will get the general idea across. So I'm going to take the original equation, just going to write it down here. And then I'm going to multiply both sides by 6x by the LCD. Now remember, what happens then is that LCD is going to distribute to every single term. So you're going to have 4 over x times 6x minus 5/3 times 6x equals x over 6 times 6x. And what happens here is, remember, we can always put these fractions over 1. The x will cancel out with the x there. The 3 will cancel out with the 6 and make it a 2. And over in the last one, the 6's cancel. My denominators are all gone. And so now I'm left with 24 minus 10x equals x squared. Now I just have a quadratic equation to solve. And that's the idea. I'm going to go ahead and just finish this up real quick. Make one side equal 0. We'll factor it. X plus 12, x minus 2. Set each factor equal to 0. And x is negative 12 or 2. So again, what we did was we found the LCD, multiplied both sides of the equation by the LCD, and that's going to cancel out all the denominators. The idea is to have an equation that has no fractions in it, and then you go ahead and solve. Now the one thing you have to do here, this is another place you have to check for extraneous solutions. But this is not a full check like the radical equations. All you have to do is, let me write this down first, check for extraneous solutions. In this case, all we need to do is make sure no denominator, oh my goodness, I can't spell, denominator will be 0. So in this case, we got negative 12 and 2 for an answer. Going back to the original problem, this is where our variable was in the denominator. But when x is negative 12 or when x is 2, we won't have a 0 in the denominator, so they're both keepers. But you just have to do a check like that. It's a visual check if you want. You don't have to show the work for it. All right, so let's do a couple of other problems, and then we'll move on to our last topic. Okay, so based on what we covered in the previous problem, if you want to try this one on your own, feel free. Pause the video, and we'll take a look at it together in a moment. All right, so then we get this one. So let's take a look at it. Again, you should always factor your denominators if they factor. This one doesn't. So there's your LCD right there. Both sides of the equation get multiplied by the LCD. When the LCD multiplies by this fraction, the x plus 1's will cancel, so you're left with 4 times x plus 2. And then on this side, when the LCD gets multiplied by this fraction, the x plus 2's would cancel, so you're left with 3 times x plus 1. And then, of course, 1 times anything is itself. So that's the key getting to this line. But once you're here, now it's pretty straightforward. We're going to distribute the 4, distribute the negative 3. We're going to multiply these guys together, make one side equal 0, factor if it can. If it can't, use a quadratic formula or something like that. And solve, double check for extraneous solutions, but neither one of these. Make the denominator zeros, so you're good. And there's your answer. Okay, one more of these. Okay, here's our last one of these. Again, go ahead and give it a shot and we'll take a look at it together. All right, here's this one. So again, always factor the denominators if they can. This time it can. This one's difference of squares. So our LCD is just going to be x plus 2, x minus 2. And then once you got that, multiply both sides by the LCD. When the LCD multiplies by the first fraction, the entire denominator cancels out with the LCD, so you just have 5. With the second fraction, the x plus 2's cancel, so you have 2 times x minus 2 left. And then nothing cancels out on the end. And then it's just a matter of distributing and making one side equal 0. I was left with something that didn't factor, but a is 1 and b is even, so I completed the square. You could have used quadratic formula if you wanted to, but completing the square I thought was much easier. Remember, separate the variables from the constants, so I put the 5 back over here, and complete the square by taking half of b squared, so add 1 to both sides. I get 6 equals x minus 1 squared. Take the square root of both sides, add 1, and there's your answer. And then this will definitely not make any denominator equal 0. So we're good. All right, last thing, absolute value equations. These are really straightforward. All right, let's take a look at this. So let's say you've got that. So basically what's happening here, we have an absolute value that equals a number. And in order for the absolute value of something to equal 10, whatever's inside has to be positive or negative 10, because the absolute value of negative 10 would still be 10. The absolute value of positive 10 would be 10. So essentially what you do is you isolate the absolute value and then take what's inside and you make it equal to positive or negative. You make two equations out of this. You often get two answers. Sometimes when you make these two equations, you get the same answer out of them, but often you get two separate answers. Then we just solve. Add 1 to both sides and divide by 5, so we get 11/5. Add 1 to both sides and divide by 5, and we get negative 9/5, and there's our answer. X is 11/5 or negative 9/5. And it's that easy. Okay, so let me give you one to try, and we'll see how it goes. So let's see, let's do the absolute value of 4x minus 7 minus 3 equals 11. So you give this one a shot, and we'll look at it together in a moment. All right, so there we go. The only catch here was you had to remember isolate the absolute value first. So you do want to add 3 first onto both sides, but then make two separate equations. By the way, notice when I'm making the two separate equations, like think about what's going on. We know whatever's on the inside has to be positive or negative 14. There's no more absolute values here. But don't drop the absolute values until you are making the two separate equations. People either drop the absolute value too soon or keep bringing it down when they shouldn't. And I will take off if your work is not mathematically correct, even though you get the right answer. You're not going to get full credit on the problem. I give partial credit, but your work has to be correct as well. Okay, let's got 2 more problems and we're done with our notes. Okay, here's something to noodle on. See if you can figure out what would happen here when you have 2 absolute values. Okay, so I just put a simpler problem over here on the right-hand side. Let's say you had the absolute value of x equals the absolute value of y. If we follow these steps exactly, we know whatever's on the inside has to be the plus or minus of this side. So that means that x is either the positive absolute value of y, or x is the negative absolute value of y. Well, now we have absolute value equations again. So looking on this side, if I were to split it into 2 equations, it would be y is equal to the positive x or y is equal to the negative x. So I have this. Over on this side, remember you have to isolate the absolute value first. So if I move the negative over here, and then take the plus or minus, Well, positive of a negative x is positive x, or sorry, it's negative x, but negative of a negative x is positive. I'm still left with plus or minus x. So the bottom line is, if you have two absolute values, don't worry about it. You essentially have the same kind of thing. What's going to happen here is we're going to take, it doesn't matter which side you do this to, but you're either going to say, like, we could take the left-hand side is equal to the positive of the right-hand side, or is equal to the negative. This is running together. I'm going to put a little barrier here. Sorry about that. So we have these two separate equations. So you still split it into two. Don't think of it as any more work. You're just going to take what's inside and make it either to the positive of that or the negative of that. And then you work it out. So now we just have two separate equations. Let's just keep going. All right, so over here, let's say we subtract 5x from both sides and add 1. We get x is equal to 3. And then over here, I'm going to distribute the negative first. And then add 5x and add 7. So x is going to be 7/4. And there's our answer. X is 3 or 7/4. All right, we're done. One more example. Okay, here's one last example. Try this one on your own, and we will come together and see what we get. All right, here it is. Be careful, this one was a trick question. Okay, so you're still going to solve like normal. You want to isolate the absolute value, so we're going to subtract 5 from both sides, and we get this. But now look what you got. We have the absolute value is equal to a negative. That can never happen. You can just stop right there and say no solution. So remember, if you ever have an absolute value equaling a negative, be on the lookout for that, and just jump right down to no solution, and you're done. All right, that was a lot of examples to go through. So if you stuck through the whole video and watched every single one, well, you're a trooper. All right, I'll see you in class. Bye.